As we should know, a trapezoidal approximation graph consists of an approximate graph of a function. If we start with the curve of our function, we can mark x values at equal x intervals, and then we can put y values on the vertical lines and values of the slope in boxes above the various segments at the tops of our trapezoids. Now we could get this, let's suppose this is obtained by evaluating our y equals x to the p function at our x values. That would be here, 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 etc. Okay, so we're going to have actual numbers on a trapezoidal approximation graph. Now, having constructed that graph according to the numbers using very possibly mathematical software, we'll have a physical graph that we could print out and actually use to construct a slope graph. And we could construct a slope graph easily enough, an unscaled slope graph, just using our compass. Okay, the rise, since these x values are presumably equally spaced, as we've seen before, the rises can be used as our values of the slope function. Okay, since this is our slope graph, of course, the values of our slope function will be the rises. So I could construct a line segment here congruent to the line segment I have here. Now I locate that segment at the middle of this x interval simply because the slope from here to here is going to be pretty close to the slope of the actual curve at the middle of the interval. Now there's no guarantee that the point of tangency will occur at the middle of the interval, but if the function isn't too wild and our x intervals are small enough, it's going to be pretty close. Okay, so we've got a value here, and then we can come up here and we get a value here. Corresponds to this, and so forth. Now, our slopes are going to get pretty small. By the time we get out here, we're going to have a point that's only about here. So we might choose to double, even triple these values. Let's see, can we triple that? We get up pretty high. I can just double these x values and get something like this, and double this one, and the trend will be something like this. So this would be an unscaled slope graph. Then, since we do have numerical values of our slopes, we could assign whatever the numerical value of this slope is to this point and scale our y-axis. So assign the numerical value of a chosen slope to the corresponding point on the slope graph, and this implies a scale for y. Now we've already got a scale for x because we've got numbers on these x values, so now we have a perfectly good slope graph. Of course, we could also construct the slope graph by just using the numbers of our slopes. Now I've got these rectangles here. We should understand that these rectangles indicate slopes. That's the convention for a trapezoidal approximation graph. That's something we use just in this course. Don't try to take it out into polite society and expect anybody to know what you're talking about unless you explain it. Okay, so we could have constructed these things according to some scale and used the numbers in these boxes to construct our points. I kind of like the idea of constructing it geometrically, but if we really wanted it to be accurate, we'd go ahead and use the actual computed values, the values which we've presumably computed from the x values we get, x and y values we get, especially the y values that we get by evaluating this function at the various x values. So I simply say that one way or another, if we have the numbers, we can scale our slope graph, and if we do that, then we can figure out the precise function ax to the p. How do we do that? Y equals ax to the p. Plug in values of 2 points, and say the x and y values of 2 points to get 2 simultaneous equations for A and P. Solve. Okay, we've seen this. So there's just some perspective on one of the really pretty neat things that we could do with a trapezoidal approximation graph. And we could get some real evidence of how the power of the original graph is related to the power of the slope graph. So I'll say that's good evidence for the relationship between the powers of the original and slope graphs. And of course we could do something very similar with asking different questions to construct the slope graph of an exponential function for a given value of b. We could actually investigate what kind of values of b give us slope graphs that are identical to the original graphs. So value b such that the slope graph is equal to the original. Very interesting question. If we can do that, then, well, clearly the values would be the same at the y-intercept, and that would give us evidence for that holy grail number b that we've been looking for.